All right, so hi everyone. My name is Sahil. I'm a PhD student with Sriraam. I work on the topics, broadly the same topics that I'm presenting, right? Deep generative models, probabilistic deep generative models, right? How you can utilize the power of a generative model in making downstream inference tasks, making decisions in real life applications in a more reliable and robust manner, right? Well, before I begin, maybe I'll confess that I'm not as energetic as Sriraam is. So if you are, having listened to his talk yesterday, if you are hoping for something similar, you might be in for a bit of surprise. But I'll try my best, but we'll keep it interactive, as much as interactive as possible, right? So the same rules as yesterday applies, right? You can interrupt me at any point to ask questions. And we'll take a break, like a 2-minute break, 40 minutes or so into the session, right? Okay. So let's go. All right, so in today's talk, yesterday we looked at some of the foundations of what are called probabilistic graphical models, which were a classical way of looking at probability distributions, how people have looked at how you can represent the probability distribution and get answers from it by running inference, right? And they had the graph structure and parameters associated with them, and we saw all that yesterday. But what we also saw is that in the general context where you do not have any additional structure imposed over those models, inference itself is like NP hard, right? And these models do not scale very well when it comes to very high dimensional data distributions, like over images, over texts, etc. very well, right? But you know that we live in a world where deep generative models have taken over, right? And almost everyone now knows about LLMs and generative models. And when you talk of a generative model, that's typically what comes to your mind, right? So we have seen these examples where you have fake images, fake videos, even all sorts of things that are generated by an AI, which you cannot really distinguish from what is generated by a human, right? So what we will do today is we will take a look at some of such deep generative models. We did not talk of anything deep yesterday, right? And the title of the workshop is Probabilistic Deep Generative Models. And I understand some of you might have just come looking at the deep part, right? But we will look into some of the deep generative models today. And but we will take an inference perspective where we will try to see that are these deep generative models in fact tractable for probabilistic reasoning and doing things that we discussed yesterday, right? So we will formally define the notion of what tractability for probabilistic inference means, right? And what do probabilistic inference itself mean? Right? What sorts of queries are we referring to when we say probabilistic reasoning? And then we'll come up. I'll sort of set up the motivation as to why you need a model that can not just generate data but can also be used to reason about the underlying distribution. That will bring us to the notion of what are called probabilistic circuits, which are a class of models which are expressive to model complex distributions, but can also do probabilistic reasoning tractably and exactly, right? We'll take a break somewhere in between, and then we'll also talk about how you can learn these models. All right, so I'll start from something we already discussed yesterday, right? That is the high-level notion of what a generative model does, right? So what comes to your mind when you say generative modeling? So everything in this world, you can think of it as a random variable, right? And if you're interested in generating or understanding the process that gave rise to the data that you see around you, you can sort of think of it from a probabilistic sense as there is some probability distribution over the set of variables, or over the set of values that all those random variables can take. You do not know what that underlying distribution is. So in this case, for example, so you only have access to some data points, which could be like faces of people, right? But it's coming from some underlying distribution. And the goal in generative modeling is to find a model that closely approximates your true data distribution, right? But it's an ill-posed problem, like Sriraam said yesterday, because you do not know what the distribution is. You only have access to samples, right? And you need good samples, good data that is representative of your distribution if you really want to learn the distribution back from your data. All right, and deep generative models have been very popular, right? So if you look at this slide, all of these images on the screen you see are faces of people generated by an AI algorithm, right? These are not people that exist in the real world. And it's really fascinating to see how much these models have progressed, right? So deep generative models, they can synthesize data, they can generate new data points, which are sort of indistinguishable from real data points, right? That is something we know, we have seen so far. But the question that we will ask today, I mean, you have also seen this in the context of text with all the large language models, ChatGPT and whatnot, right? That they can generate very plausible text outputs. But the question we'll ask today, and like the focus of this tutorial is not in building systems that can just generate samples. Generating samples can be useful in certain cases, right? But the true power of modeling the probability distribution underlying a system's variables comes from the ability to use it to reason probabilistically and make decisions that are reliable and grounded in the theory of probability, right? So we'll ask the question, can they reason probabilistically? And we will build a class of models that can do that. All right, so many of you might be wondering, well, I have seen this large language models. I use ChatGPT all the time. They seem to be doing some sort of reasoning, right? Why can't they do probabilistic reasoning? Or can they do probabilistic reasoning? If so, why do I even need to listen to this talk, right? So I was just playing around with ChatGPT yesterday. So I gave it a question, right? This is typically like one of your high school questions in which you're given a lot of things, but you don't really need all of them, right? There is some part that is important, and you have to figure that out and solve the question. So it's a simple question. Let's say that Sriraam is visiting IIT Madras for a talk. He is, actually. The talk is post-lunch. So his first talk was post-lunch, which is why I made this. And people are typically sleepy with, say, a probability of 0.6 after having a heavy meal. I hope none of you had a heavy meal. And only 20% of the attendees have some background about the talk. And even people with background have, let's say, 30% chance of not falling asleep, right, post-lunch. Now, Sahil is attending his Sriraam's talk. I have some of the background. I have all the background for the talk. But I've also had a heavy lunch. Now, what is the probability that I will fall asleep during his talk? If you look at this, OK, anyone wants to go ahead, solve this? It's, you guys can take a, go at this. It's not very complex. So if you look at the question, it clearly says that people with the background knowledge for the talk and who have had lunch. Let me see if I can. Is there a pen somewhere? Oops. Okay. Yeah. So you say that people who has the background and they have also had lunch, the probability of not falling asleep, which means asleep equals false, is what? 30%, 0.3, right? So what is the probability of falling asleep? 1 minus 0.3, which is 0.7, right? Which is why we had the talk before lunch, right? But so if you think about this, this is something very easy for you to solve, right? Now let's ask the same question to ChatGPT and see what it comes up with, right? Now, so ChatGPT, when you ask this question, it comes up with a very fascinating and impressive set of steps that it performs to do reasoning, right? So it makes it puts up a picture that it is doing something very complex and it is doing probabilistic reasoning. But if you closely look at it, it's sort of doing nonsense, right? What it's doing is it has seen examples of queries in which it has been asked to compute probabilities like this, right? And typically in those questions, it knows that you have Bayes rule applied somewhere, so it tries to apply Bayes rule. It does a whole bunch of calculations and things, and at the end, it gives you the answer that the probability of Sahil falling asleep is 1.05, which is crazy, right? Because a probability cannot be more than 1, right? So these models, they give you the impression that they might be doing probabilistic reasoning, but they are really not, right? So if you ask the question, can they reason probabilistically? Not really. By the way, this is you can play around with ChatGPT. I haven't checked with ChatGPT 4.0, but this is what ChatGPT 3.5 gives. So they cannot really reason probabilistically. And there have been recent papers. So there's a recent paper in ISCAI 23 that looks at large language models and their capabilities to do logical reasoning and probabilistic reasoning, right? And the conclusion with solid experimental evidence is that just a model that has been trained to achieve high accuracy on in-distribution examples, it has not learned to reason. So even if you train a model, if you give it data, logical reasoning questions as the input, and you have the answers as the output, and you train the model to find the mapping or do the translation and reason, such a model cannot really learn to reason. What it can only do is to use statistical features to reason about, to make predictions rather than to emulate what is the right reasoning function. So what does that mean? So in the previous example, you saw that it has seen that in questions that involve computing probabilities like this, where you're given some things and you're not given some things, right? So it has seen examples where people have used Bayes rule. So it has some knowledge of statistical correlation that it has to use Bayes rule, but it doesn't really know what is the right reasoning function to use, right? So these models, at least as of now, they cannot do correct probabilistic reasoning or even logical reasoning, right? So the point, so this in this tutorial, sorry.
So you use the term reasoning function.
Yeah.
What is it that you're
So it's more of how we reason, right? So there is a set of steps that we follow to come up with the final answer, right? So you can think of your reasoning steps. You can sort of write it down as a program if you want, right? So I compute this first, and from there I do this, and we have a prior about what is the right reasoning step to use at each step, right? But a machine learning model cannot, or at least these models, they do not have the ability to do that. They can look at what they have seen, statistical correlations between what they have seen previously, and do something similar, but they cannot exactly emulate the right reasoning function when you have a test data point. Right. All right, so thus the focus in this tutorial is to build what are called deep, tractable probabilistic models like we said yesterday. We want them to be deep because everyone likes deep learning. It's very popular. It's very powerful as well, right? You have neural networks as like flexible function approximators and stuff. But you also need some sort of tractable models because you're interested in doing probabilistic reasoning. And this talk would be at the intersection of everything, right? Where you want deep models which can do probabilistic reasoning efficiently and tractably, right? That's the whole point of this tutorial. So the key question that we will ask is how we can build probabilistic generative models that can fit complex data distributions, but also reason about whatever uncertainty is involved with the variables that you're modeling, right? In a good way. Now, why probabilistic models? Definitely. So everything in the world you can think of, my view is it's a random variable, right? There's always uncertainty involved with everything that you're modeling. Your data is uncertain. Your model itself can be uncertain, right? There's uncertainty in different steps of your modeling process. And probability theory is sort of the best principal way we have to deal with uncertainty, right? Now, when you build such models, they are like models that know what they don't know as well, like Sriraam was mentioning yesterday. We are not just interested in models that know what they know, right? But they should also have an idea about the uncertainty over the things that they do not know, right? So such things can be incorporated in a probabilistic model, so they are robust. And yeah, probability theory gives you language to actually query and convert the things that you're interested in computing from natural language into probabilistic queries. So tractability, it's important because, like Sriraam was saying yesterday, it gives you a sense of explainability because now you can query the model based on things that you're interested and see what the output is. You can sort of have a view of what is it that the model is looking at to make decisions and things, right? So the class of models that we will discuss, they will also be like computationally efficient, and you can deploy them on GPUs. We'll come to that, right? And most importantly, the things that we are computing, they are exact with respect to the distributions that you have. We do not need any sort of approximations because when you deploy a model that has approximations, you do not really know what error it will make, right? So you need exact inference algorithms and exact computations. So the key idea is that these deep, tractable, probabilistic models, they can answer complex queries over like distributions in high-dimensional spaces exactly by leveraging some of the advances in deep learning. So with that, I've been talking too much about tractable probabilistic models and probabilistic inference. Now let's try to sort of ground this in the same like setting that we discussed yesterday, right? So Sriraam went through most of what we will cover, but this will be something that comes up again and again. So I thought it would be good to have some more emphasis on this, right? And lay it out for you in a bit more detail, right? So let's consider the example that we looked at yesterday, where we are interested in a healthcare domain, where you're interested in modeling risk factors that affect adverse pregnancy outcomes, like preterm birth, gestational diabetes, etc. Right? So this is an important problem because like he said, even in India, 15% of the births are preterm, and this is also an issue in the US, right? So if you look at a setting like this, what does your data looks like? So like we saw yesterday, you typically have features such as, say, BMI, age, you have lab tests coming in, you have socioeconomic factors, etc. Right? And you're really interested in building a model that understands how each of these variables correlates with each other and that you can use to reason about different aspects, right? Without training individual classifiers for each query that you're interested in, right? By the way, am I going too fast? Am I talking too fast? You can interrupt me and ask me to slow down. I have this habit of speeding up. Okay, so like what we'll do is we'll consider probabilistic generative models over these random variables, right? And we will sort of write down what the different probabilistic reasoning queries might look like, right? So in the simplest case, you have what is called as a probability mass function or a probability density function if you have continuous variables. What does a probability mass function look like? Basically, it's an assignment of a probability value to each value that your variables can take, right? So you can think of it in terms of this giant table in which you have each possible combination for your variables, and then you have the corresponding likelihood assignments, right? So if everything is discrete, you have what is called a probability mass function or a PMF. And as you know from like basic probability, all the values should be between 0 and 1, and they should sum to 1, right? Now, okay, so coming to inference queries, right? So the first inference query or the class of inference queries we will look at is called evidential inference. Now, what evidential inference boils down to is in computing what is the likelihood associated with a complete assignment of values to your random variables. So in this case, you have things like BMI, GDM, age, family history, etc., right? So if I have a probabilistic model over these variables, and I have a complete assignment of values. So I'm interested in computing the likelihood of a particular entity in that table, right? So I assign values to each of my variables, and I ask the question, what is the likelihood of observing such a data point, right? So for this case, what is the likelihood of observing, say, a 35-year-old pregnant woman with gestational diabetes, having a BMI of 20, and a family history of diabetes? That is how it looks like in natural language, right? But in terms of probability, it boils down to computing this particular query. So we'll refer to this as evidential inference, right? So we will define like these terminologies so that we can look at different models and if they are tractable for these queries, right? So that's evidential inference. Now, marginal inference is also something we saw yesterday. What is marginal inference? Now, when you are interested in reasoning about a subset of your random variables, you're not really interested in, or you really don't have an assignment of values to all the variables that you have, but rather a subset. So in certain cases, say, family history might not be available. In certain cases, lab tests might be expensive and the patient might not have done it, right? So if you have a model that is defined as a whole over all the variables that you have, and at test time, you do not really have information regarding some features, how do you handle it in a probabilistic way? And that is where marginal inference comes in. And what marginal inference does is it looks at the likelihood of a subset of variables, right? So what you have is you have this joint distribution over 4 variables, but you really don't know what the value, let's say, family history takes. So what do you do? Okay, you look at all values that family history takes, and you take a summation over it, right? So you marginalize out the unobserved or missing random variables. So that's marginal inference. Now, why did we do a summation here? We did a summation because it is a discrete variable, right? If it was a continuous variable, you would be integrating it out over all the set of values that continuous variable takes, right? So does this make sense? Do you have any like sort of doubts regarding what marginal inference is or why we are doing a summation, etc.? Good? Okay. All right, so that was marginal inference, right? And the same applies irrespective of how many random variables you have unobserved, right? So if you have, say, 4 random variables unobserved, you will be summing over or like integrating over, if you have a continuous variable, over all the values, all the missing variables takes place, which is a complex task because it can grow exponentially when you have a large number of such missing variables, right, in the classic sense. So we'll look at approaches that enable you to do this marginal inference tractably. Now, the third type of inference query that we are interested in is what is called conditional inference, where, okay, you are given that certain things in your state space or certain things, you know that certain things have already happened right? You're modeling a system, and you know that certain things are already true. Now, how does that influence your belief over the remaining set of variables, right? That is where you ask the question, given that certain variables take a particular set of values, what is the likelihood of observing value for the other remaining variables, right? So, for example, what is the likelihood that a pregnant woman has gestational diabetes given that she's 35 years old, has a BMI of 25 and a family history of diabetes, right? So, this boils down to writing conditional queries, and from base rule, we know that we can write P of A given B as P of A comma B divided by P of B, right? And what P of B is, okay, let me write this down. So, you have from base rule P of A given B is P of A comma B divided by P of B. Now, what is P of B? If you are looking at a model that has, if you're looking at a joint model over A comma B, how do you compute P of B? Well, we just saw in the previous slide that this is basically a marginal inference query, right? You're marginalizing out A because A can be thought of as unobserved here. So, you sum over all values of A, P of A comma B. So, conditional inference involves marginal inference as a subroutine, as you can see, right? So, anything that is tractable for like marginal inference would also be tractable for conditional inference, marginal and evidential, right? So, that is conditional inference. You can also think of more complex reasoning tasks. So, for example, I can ask, okay, given this probabilistic model, which age group and BMI values of women having family history of diabetes is most likely to develop gestational diabetes, right? Now, what you're interested in doing is you're interested in looking at this distribution and looking at values of certain variables that maximizes the likelihood of something happening, right? So, in a mathematical sense, it boils down to computing what are called argmax, or the argument or the variable values that maximizes this particular probability, right? So, for in this case, you'll be maximizing over the values of age and BMI from your joint distribution, right? So, it involves finding some sort of maxima of your probability distributions. Sure. So, this class of queries, we call them as map inference queries or maximum a posteriori inference. You can also have, now you can mix, yeah. So, in evidential inference, you are asking the question, how likely is any particular, what is the uncertainty associated with a complete assignment of values, right? Now, you're right that, you know, in conditional inference, it is also somewhat similar, where you say that I'm given that certain things have already happened, right? And that is proportional to the joint assignment from base rule. So, P of A given B is proportional to P of A comma B, but there's also an additional P of B given term in the denominator, right? Right? So, think of it like this. You have, let me write this. So, let's say you have something like this in Venn diagrams, like you have A and B. Now, when you know that nothing has happened a priori, like your data can lie in anywhere, but if you say that B has already happened, right, then anything in A can only happen in here, right, because B has already happened, right, things like that. Okay. So, just to give an overview, so the key idea in this, like in the previous couple of set of slides, is that many of your reasoning tasks in natural language can be in a probabilistic way written down as some form of queries, querying the model. So, things like how likely is an assignment, how likely is a partial assignment, right? Given certain values of your random variables, how likely is the remaining variables, what is the most likely assignment, and you can come up with such queries which are, you know, important for the task you are modeling, or like for the application you have. You can write them down as some computation defined over these joint distribution that you're modeling, right? And when we say we need a tractable model, what we are really saying, okay, what is tractable probabilistic inference? What we're really saying is that a class of queries, so like the queries we have seen so far, you call them as tractable on a class of models, let's say M, if and only if the answer to those queries can be exactly computed in polynomial time. So, if you have a model of size, let's say M, or if M is a model, right, and if you can, if you have a set of queries that you're interested in computing, and you can query your probabilistic model M and get exact answers to it in time that is polynomial in the size of your model, then you say that the model is tractable for that particular query, right? Now, there are a couple of interesting things here, right? Because So tractability, if you think about it, it's not something very objective. It's more like a spectrum, right? So you have queries that that could be more complex, right? You also have models that might not have a lot of structure, right? So tractability depends on both. It depends on what query you are interested in computing, and also what class of models you are building, right? So you need to find appropriate structures for your model under which certain queries become tractable, right? So that will be the focus. How do you define structures over your model so that the query you're interested in computing becomes tractable for you? All right. All right. So now let us look at some of the existing generative models and see if they can do any of these tasks tractably. So if you take a very high-level picture of generative models, right? So you have the classical approaches to generative modeling, some of which we discussed yesterday, like Bayesian networks, Markov networks. You have mixture models, and in deep generative modeling, what's popular are things like GANs, variational autoencoders, normalizing flows, autoregressive models, diffusion models. We'll come to some of these in a bit more depth, but I just wanted to lay out the field for you here, right? So we'll discuss like at least 3 of these deep generative models and see if they are actually tractable for some of these inference tasks, right? And what you will observe is that most deep generative models are not, and some deep generative models can compute some inference queries tractably, but not more complex ones. That would be what we are trying to arrive at, right? All right, so before that, so what is your notion when I say of a deep generative model? So the deep part gives you some intuition that it has got to do something with neural networks, right? We all know neural networks are universal function approximators, right? And if you have things like, so if you're really interested in modeling a mapping between 2 spaces, you can effectively do that with a neural model if you have inputs and outputs, right? So so let's say, so when I see something, let's say an image of an apple or like an apple in front of me, I have some sensory input coming into me, right? And there is some mapping that maps that into my understanding of what an apple is, right? So in a similar way, you can abstract out what is the function that does the exact mapping, right? And if you're given inputs and outputs, you can sort of learn what is the function that maps this input to the output using something like a neural model. But what you would need in such a case is supervised data, right? You would need, okay, which outputs correspond to what inputs, right? If you have that paired information, then you can approximate the mapping using a neural model. And these are deterministic functions. But when you talk of probability distributions, you have randomness in them, right? You're talking about stochastic processes. You are talking of generating things, right? So if you have a deterministic model, how do you generate things from such a model, right? That is an important question. And the issue is, unlike supervised learning tasks, where something like a classifier, where you know what the labels are corresponding to your inputs to train the model, in generative modeling, you do not even have access to the underlying distribution, right? So if you have access only to samples, and you're interested in modeling the real distribution, you cannot do that in a supervised way like how you train a neural model, because you do not know what the true underlying density or probability is for any given sample, right? So then you need to come up with ways to approximate these, and that's what most deep generative models do, right? So at a very high level, what the way I like to put it, sorry. So these models, many of these models can be broadly classified under what are called deep latent variable models, right? So what you think, if you think about any data distribution, there's a hypothesis that says that the true factors of variation, so when you're talking of a generative model, right, there are factors that cause variation in your data, right? So there's a hypothesis called the manifold hypothesis that says that the true factors of variation that underlie any system's variable are actually embedded in a low-dimensional simple space, right? So what you can now do is, okay, you assume that there are certain factors of variation. I do not know what those factors causing variation in my data are, but they lie in some lower dimensional space, right? Let's call it Z, right? Now, since this is a lower dimensional simple space, I assume it to be, I can assume some distribution over this space, something simple like a Gaussian distribution or whatever I can sample from, right? Now, if I have such a space and I know that, I can map, these factors of variation can be used to map it to the data space that I have, then I can use some sort of a neural model as a function approximator to learn that mapping, right? but still I do not know what is the supervisory information, what z corresponds to what x to learn that function, things like that, right? What I do know is that there are some simple factors of variation, and I can utilize those to generate my entire data set, right? Now, how do you learn these mapping? That is where the classical deep generative modeling like literature or like most of GANs, VAEs, and normalizing flows differ is in what supervisory signal do you use to train them, right? So let's look at a few of them. So in generative adversarial networks or GANs, what you really do is you pose the data, the problem of learning the data distribution as an adversarial game. So what you do is, okay, I sample something from a Z space. Let me use this. Yeah. So I sample something from my latent space. I use a model to transform it to my data space, right? But those data can be like very noisy. So initially when you learn, this can be just random noise, right? And I need some way of supervision to train this model. Now, how do I get the supervision from? Well, I have another model that has access to your real samples, right? And I train the model in more like a classifier sense where I give it the real samples and the samples that have been generated by my generator, and I ask it to classify whether that input is real or fake, right? So this whole problem can be formulated as what is called a min-max game, right? And it's more like an adversarial attack, right? So if you're not very familiar with GAN literature, the way I would explain it is, let's say you are interested in, say, hacking a computer. You shouldn't do that, but let's say you are interested in coming up with a password, right, for logging into some system. Right? Now you're doing some sort of an adversarial attack on the system where you say, okay, I'm trying some combinations, right? I'm trying some combinations of my password, and the system knows what the password is, but I do not know. My intention is to learn what the system knows, right? How do I do that? Okay, I come up with something that can be noisy initially. I give it to the system, right? Now, if it's a perfect system, it wouldn't give me any sort of feedback if I give in a wrong password. It would say your password is incorrect, right? But if my system, if there is some leak of information from the system to me that says, okay, the first letter is incorrect, or something like the last letter is incorrect, then I can sort of convert my input password generation task as an adversarial attack where I vary my input combinations based on the feedback that I get from the system, and then eventually I'll be able to figure out what the password is, right? So something similar here. So you have a generator that is interested in modeling the true distribution, but it does not know what the true distribution looks like, right? And my discriminator, it has access to real samples, and it can say whether an input is real or fake. So I can use the feedback coming in from the discriminator to eventually learn what the data distribution looks like for my generator, right? And the whole process is like learned using gradient descent. And this, from a game theoretic viewpoint, it's modeled as a min-max game, and there's a whole bunch of theory behind it, right? But when you have a min-max game, you converge to what is called an equilibrium, and you can prove that when you reach such an equilibrium, you will learn the data distribution, right? But the issue with things like models like GANs is that, okay, they are very, so the good thing is that they are like, you do not have any additional constraint over these models. You can have arbitrarily complex neural models as your generator and discriminator, right? And you can generate very high quality samples, right? But if you think of this, if you look at this formulation, there is nowhere that we are defining any sort of likelihood. You do not have any access to your underlying data distribution that the model is like modeling, right? So then when it comes to things like probabilistic reasoning, you do not have a way of answering queries, right? So these models cannot reason. They are what are called implicit density models, in the sense that they model the distribution implicitly without giving you any access to it, right? And there are other issues with this, with GANs, that they are highly unstable to train. I used to work on GANs when I was in my bachelor's, and it was a nightmare to train these models. But people have come up with like things to stabilize their training and stuff. And in a lot of cases, what it involves is imposing some sort of weak structure over these models, things like Lipschitz continuity, spectral normalization, etc., over these models that help stabilize your training of these models and generate good quality samples, right? But if we look at the queries that we defined earlier, which are like evidential inference, marginal inference, or this should be marginal or conditional inference, map inference, and marginal map inference, right? So again, does not allow you to do any of these, right? Why? Because it does not give you an access to the underlying distribution anyhow. You are not explicitly modeling P of x anywhere, right? So you can generate samples, but you cannot use them to reason, do any of those probabilistic queries that we discussed. Okay, now let's come to another class of deep models, which are variational autoencoders. So in variational autoencoders, what you say is that, okay, I know that if I have some latent distribution in my Z space and a neural model that maps it to the X space, what I really need is some sort of supervision. So if I know that which latent factors correspond to my given data point, then I have a way of learning this entire process, right? So I do not a priori know what factors or latent factors causes the variation, or like what are the latent factors given a particular image, right? But if I were to assume that I can train a model to learn this mapping from my input space to my latent space, right? Then you can, so this is more like what you call as a variational approximation. So you have a true posterior distribution over Z given X, which is the latent information given any data point. If you know this, then you can learn the mapping X given Z easily because you have some sort of supervision. But if you don't know that, you assume that this is something that can be learned. You assume some sort of parametric form for this distribution, and which is called a variational approximation to this, right? And you train the model on what is called a lower bound on your log likelihood. So in this formulation, what you really get is not the exact likelihoods, but you have a way of coming up with something that lower bounds your data density, right? So you do not still have access to the true probability mass function or density function, but you have something that is that lower bounds it, right? So you have some notion, but still you do not have an explicit way of computing any of those probabilistic queries, right? So I'll skip this. So if you look at the probabilistic queries again, what we'll see is that, okay, evidential inference, what did it involve? We had to compute probability, exact probability. We had to compute the probability of a complete assignment, right? So P of X. So can you compute P of X using a GAN? You cannot. Can you compute P of X using a VAE? Well, you cannot exactly compute P of X, but you can compute something that lower bounds P of X, right? So you can compute some L, which is a lower bound for your P of X, which is also not very useful in many cases. Now, a recently developed class of models are called normalizing flows, right? And interestingly, these are also neural deep generative models. But what you do is, okay, so I was talking of this supervisory signal that you need to learn this distribution, right? So you do not know what is the Z that generated an X, right? But if I were to come up with a neural model that is invertible, so at the end of the day, you can think of a neural model as a function, right? So if the function is invertible, then you can go back and forth, right? You can go from your latent space, your data space, and you can come back from the data space to the latent space, right? So you can go back and forth if you have an invertible model. Now, what exactly do I mean by an invertible model, right? So if you have f, if you write it down mathematically, right? So the forward pass would be like you have x, you use a neural network to compute f of x. Now, given f of x, can I get x exactly without any information, which is f inverse of f of x, right? Which would be x. Now, interestingly, if you have a function that is invertible, then you can use what is called the change of variables formula to map the probability density in both spaces. Now, we'll come into more details of how a normalizing flow looks like, and it works in tomorrow's like talk, because so if you look at this, you have this change of variables formula, which gives you a way to exactly compute probability density, right? So this is a deep neural model which is tractable for something. What is it tractable for? It is tractable for doing evidential inference, right? So you can compute what is the likelihood of a complete assignment of values. You can compute what is P of X using something like a normalizing flow. But you cannot do something more complex. You cannot integrate out things. You cannot do summations over things that you're interested in, right? So things like marginal inference, map inference, marginal map inference, those are intractable even for a deep generative model like a normalizing flow, right? Okay, let me pause here. I know this might be like a lot of content in like 10 minutes, but the point is not to give you how each of these models work, but to make the point that, you know, there are deep generative models out there, right? You have different ways of parameterizing and training them, but they cannot really be used for the type of probabilistic queries that you're interested in, right? So if you're not understanding like the concepts or theory behind how these work, it's okay. We can talk later if you want, but I hope you get the point, right? That, you know, you cannot use these models for performing probabilistic reasoning tasks that you're interested in. And we'll come to normalizing flows in more detail tomorrow. All right, now we also saw the classical machine learning models like Markov networks and Bayesian networks, which we discussed in detail yesterday, right, which gives you a way of parameterizing a probability distribution in terms of a directed acyclic graph, right? You have local conditional distributions and you take a product over your local conditional distributions to generate your joint distribution. It's basically using the chain rule of probability with some factorization notions, right? And what you saw is, okay, you can compute certain things tractably. You have a way of evaluating p of x, which means evidential inference is tractable, right? And we saw that when you have additional structure, like when you have a tree structure, let's say, then things like computing marginals and conditionals also become tractable, right? So if I try to put Bayesian networks and Markov networks in the same view as those deep generative models, you can see that in the general case, Bayesian networks are tractable only for evidential inference. But if you have additional structure, like a tree Bayesian network, then like we said yesterday, you can use notions such as caching and dynamic programming and belief propagation and stuff to do inference exactly and tractably, right? When you have things like a tree structure, right? So when you have tree structured Bayesian networks, more things become tractable. And this is also something that we have been seeing. So you saw that training deep generative models is also unstable, and in many cases you need some structure imposed over them to make their training stable. In a similar way, even in classical models, you need additional structure to make inference tractable for these models, right? So structure is something common, and we will come to structure in more detail later. But I just want to give you an idea that when you build generative models, structure is something that is inevitable if you are interested in doing probabilistic reasoning. All right, now I can think of something very, very simple, like I assume a fully factorized model where I say all of if I have x1, x2, xn, right? I assume that there are no edges in my model, everything is independent, in which case, how many parameters do I have in a network? I'll just have n variables, right? One corresponding to each, if it's a Boolean variable. So this is a very highly structured model where you're assuming everything is independent. So when you have such a very restrictive structure, then all the queries become tractable because they boil down to the linear time inference. Everything is independent and you can do it independently. So if I were to put everything together in one slide, right, what is it that I'm trying to convey? A common notion, like the important notion here, is that structure is what enables you to achieve tractability, but it affects expressivity because these classical models, they are not as expressive as your deep models. You cannot generate very good quality samples from them, right? Now, if I were to make a 2D plot where I say along the x-axis I have expressivity and along the y-axis I have tractability, right? And as I'm going from left to right on the x-axis, I'm increasing my expressivity, and as I'm going like bottom to top on my y-axis, I'm looking at more tractability. And if I were to put all the models that we have discussed so far in this plot, what you can see is that you have these classical models which have a lot of structure in them and which are tractable for certain inference, right? So you have, as you go up, you'll see that you have an added level of structure and their tractability increases. And you'll see that you have deep generative models which are not so tractable, right, which is why they are on the lower half, but they are more expressive than these class of models, right? So the key question that we will ask is how you can improve the expressivity of tractable models. So you want to take these tractable models because you're interested in doing probabilistic reasoning. These models on the bottom, they cannot really do most probabilistic reasoning tasks, right? So you want to focus on these tractable models, but you really want to improve their expressivity so that they are competitive with what you have on the deep generative modeling side of things. So how do you do that? That is what we will discuss in the next part, right? So it basically boils down to what are called mixtures, right? So you'll be taking mixtures of these simpler models to build a class of models which we'll call probabilistic circuits. All right, so I think it's a good time to take maybe a 2-minute break, even for me. Okay. But if you have questions, I'll take now, or else we'll have like a 2-minute break. Yeah. Right. So I'll actually show that. So for deep models, like GANs, you do not have a way of showing it because you do not have you do not have a way of accessing the distribution itself, right? But the whole point in building something like probabilistic circuits is to come up with a representation that enables you to show and prove that these queries can be tractably computed. So we'll see how it becomes tractable. In many cases, it boils down to coming up with some appropriate structure under which we can show that things can be done in a polynomial time, right? So you have you make the argument that when you impose certain structure over your internal nodes in a graph, then some computations can be efficiently done in linear time or like quadratic time, right? So that's the way you argue. But for these tasks like in marginals and conditional, what does it look like? We'll see. So it's mostly summations or integrals, right? When it comes to marginals, so you need to show that these integrals can be computed in linear time.
I was referring to the Bayesian and Markov networks where we assume that the structure is a tree. Then we
Right.
are able to figure out, does it show that a certain kind of inferences are tractable and certain
Right. You argue in a similar way, where so you make so when you assume that structure, you show that things simplify. It decomposes into something that you can do in linear time. That's what you do. I think
The way you define evidential reasoning, it is basically the probability of a particular state, right? You know the
Right.
state of all, it's a fixed state of random variables,
Right.
all of them,
Right.
right? So why would you need why would you build first learn from data and then infer that? Why not just get a frequency kind of thing from the data only? It's a fully defined state. Why do you need a full distribution to get it?
Right. So the thing is, so when you talk of something simple like let's say 2 variables, 3 variables, where everything is Boolean, then your data might be sufficient. You can take a frequentist view where you say that I just need to count things and come up with the probability themselves, right? But what we are really interested in doing is scaling these models to data distributions with say hundreds of thousands of features. And when you do that, let's say even in the simple case like a Boolean variable, right? If you have say 100 Boolean variables, which is typical in like data sets these days, right? What would your state space there look like? You would have 2 to the power 100 possible assignments, right? Which is I think more than the what people typically say atoms in the universe, right? So it's not possible for you to even have that many data to train your models, right? So the state space sort of grows exponentially when you have more variables, right? And taking a frequentist view is not possible because you won't have data for each assignment, right? So that's the whole point. So how do you make assumptions and what approximations do you do to do things tractably? Yeah.
If you were to build a Bayesian network on the same data, you would get the local statistical probabilities
Right.
the same. So and
Right.
then
Right. So Bayes nets are tractable for evidential inference, right? Because you are assuming you are taking into account the factorizations. So the factorizations significantly reduce your state space and makes things tractable for you, right? But they are not still as expressive as a deep generative model. They cannot generate samples which look very realistic in terms of images like we saw in the deep models, right? So the question is, you need the tractability that things like Bayesian networks offer, even better tractability that like tree Bayesian networks offer, but you also need the expressivity of your deep models, right? So how do you achieve best of both worlds? That's sort of the question. Yeah. Anyone? Okay. Yeah.
in the normalizing flows.
Mm-hmm.
We had this invertible network.
Right.
So how is this invertibility helping us?
Good question, right? So the thing is, so there is theory behind it. So the way I explained it is it's more like, so if you know what your factors causing variation in your data are, right, then you can sort of use it as supervisory information to learn the mapping, right? And the way GANs and VAs does it is they have their own ways of defining that supervisory information. In flows, it's more like you use the same model to go back and forth. So and if I were to explain it, think of it like this, right? So you have what you're really given is samples from some unknown distribution, right? And you can think of, so you have you have some space, right? You have some data space, right? Now I have some function that transforms this space in some way into something that is simple. So I'm thinking of the direction where I'm going from x to z, right? So I'm warping the space in some way that my distribution looks like something like a Gaussian, right? So you have some distribution over your data points in the original space, and when you have some function that transforms this space, what you're really doing is you're expanding or stretching the space so that it looks something like a Gaussian. Now, the Gaussian is something you know the PDF for. You know what is the density function associated with the Gaussian, right? So you know what is the likelihood of any data point in the Gaussian space. You can just use the equation to compute what the likelihood is. Now all you need to do to get what the likelihood, and you have, when you have an invertible function, you have a one-to-one map, right? So for each x you have a unique z, and you have, for each z you have unique x, right? So you can link what is the density or the likelihood associated with each point in your simple Gaussian space with the density in your data space, and that is what the change of variables formula gives you, right? So we'll see in more depth of normalizing flows tomorrow, but I hope that gives you some intuition. Yeah. Okay, any more questions, or we can move forward? I don't know what time the tea break is. When do you guys want to take the tea break? 10:30, 10:40? Is that fine? Or if you guys are sleepy, we can take it. I don't know if they have tea yet, but so shall we continue? Okay, so I hope I've set up some level of motivation as to what we are going to look at, which are probabilistic circuits, which are a class of models that can do probabilistic reasoning exactly and tractably, but can also be over-parameterized and made very expressive, not to the extent of deep generative models, but to some extent, right? Almost there. That's the research part. Okay, so we are interested in looking at models that achieve best of both tractability and expressivity, and what we will do in the next 30, 40 minutes or so is in defining or trying to understand what these classes of models are. Right? So I'll talk of how do you represent distributions using probabilistic circuits, right? And we will look at those inference queries that we discussed and see how they become tractable in this case, right? Which were not tractable in deep models. And if time, and we'll also look at how you learn these models from data and what expressive deep parameterizations have been proposed in the literature to make them competitive with your deep models. All right, so if I just revisit some of the models that we have discussed. So you saw that in Bayesian networks and Markov networks, there are certain things that kept popping up here and there, right? So when you made factorization assumptions, when you were thinking of conditional independencies, you typically had some sort of products that came into picture. You were multiplying probability distributions, right? So when you have two distributions that are independent, what is the joint distribution over them? P of A comma B, if A and B are independent, it's just the product of P of A and P of B, right? So from a probabilistic sense, products from a computational perspective has some correlation, is linked with factorizations, right? And in things like Gaussian mixture models and even in some of the exponentially weighted functions that we saw yesterday, you also saw some of these summations that kept popping up, right? So then the view we'll take is, okay, you have these products and summations that keep coming up in these probabilistic models. Now, how do you build a class of models that utilizes these, right? And what we look at is utilizing sums and products to build a class of models called probabilistic circuits. Right, so I'll define what the basics are, fundamentals are for these probabilistic circuits. So at a very high level, what you're really interested in is modeling a data distribution as a computational graph. If you think of your neural models, your neural network models are also computational graphs, right? They also do some transformation, some computation over your input features to transform them into some other space, right? But the difference is they are transforming the data itself, right? They are mapping given features from one space to another space. Now, if you take a probabilistic perspective of this, and if you were to think of, okay, instead of features, I'm thinking I have some simple distributions, right? I know the parametric form for some things like Gaussian, categorical distribution, anything like that. Now, if I think of the inputs to a certain model as some distributions themselves, which are very simple, and I'm interested in transforming this through a computational graph that performs some operation in this probability space to build something more complex, right? So I'm really interested in modeling a very complex distribution over, say, images or things like that. And the way the view I take is that, okay, I can maybe decompose modeling this complex distribution as transforming something simple into it, right? So I start with something simple, some simple distributions, and then I build a computational graph, which are basically sums and products that transforms it into this complex space, right? That is like the high-level picture of what we are going to do. So a probabilistic circuit, let's call it C over variables X. It's basically a computational graph that encodes a probability distribution. It consists of three types of nodes. So at the leaf level, you have what are called simple tractable distributions, things like, say, Gaussian. At the leaf level, you have, like, you typically have one variable at the leaf level, and you have a distribution defined over that variable, right? So if you have a continuous variable, you can think of a simple distribution like a Gaussian. If you have a discrete variable, you can think of things like a binomial distribution or a categorical distribution, etc. Right? Now, the internal nodes in this graph, they are sums and products. This is product, this is sum. Right? And what a probabilistic circuit does is it defines a language to define what are called mixtures of simple distributions to compute a complex distribution. Now, let's look at each of these type of nodes in a bit more depth, right? So at a very high level, you're starting with three types of nodes, and you're building a model from this as a computational graph that approximates your complex distribution, starting from some simple distributions, right? So let's look at each of these nodes. At the leaf level, you have what are simple tractable distributions. What does the leaf node output? So let's say I have a Gaussian leaf node here, right? So the input to this leaf node would be the value assignment corresponding to the variable that the leaf node is looking at. So let's say, for example, this particular leaf node, let's say it looks at x1, right? So I'll be passing in x1, and the output of this node would be the probability associated with x1. Now, since I assume something tractable like a Gaussian or a categorical like distribution, this is something that I can compute easily, right? Because I know what the parametric form for is that particular distribution. So I can compute P of x for that input easily at the leaf level. Right? You can also have things like a simple Bayesian network as the leaf if you have like multiple variables at the leaves, right? But at a very high level, that's what you do at the leaves. You have simple tractable distributions, and the second component is the product nodes. And from a probabilistic perspective, you know that products encode independence, right? So if you have three variables, x1, x2, x3, and you're defining, so let's say this particular product node takes as input three variables, right? Three leaf distributions. So what's coming out from here is P of x1, right? From here is P of x2, from here is P of x3. Now, when you take a product over these distributions, you're basically assuming that these variables are independent, right? You're encoding some sort of independence, and we'll see that this independence helps you achieve tractability for inference. So that's what it looks like. So if you have three like Gaussian variables, three Gaussian distributions over variables x1, x2, x3, and so the joint distribution over your product node would look like Gaussian with a covariance matrix that is like an isotropic, right? Or it has diagonal covariance metric because you're assuming independence. So x1 does not have any interaction with x2 or x3 and likewise, right? So that is your product nodes. Now, the third type of nodes are called sum nodes, and what a sum node does is it represents a mixture of distributions. Right? So when you have a probability, when you have, let's say, different probability distributions defined over a variable, like let's say I have three distributions P1, P2, and P3 defined over X, which are all Gaussians. If I take a convex sum of these distributions, so what I'm basically saying is I'm taking a weighted linear combination of these distributions, right? What do I need to ensure that this combination itself is a valid distribution? Well, I need to have some structure over the weights. I cannot subtract distributions. I need to take a convex combination, right? So these weights W1, W2, W3, they should be between 0 and 1, and the weights should sum to 1, right? This is a necessary condition for so taking a convex combination ensures that the output of your sum node would still be a valid distribution. Now, to give you an intuition as to why this is helpful, right? Let's say that I'm interested in modeling a complex distribution like this, right? Now, I do not know what the probability density function is for this distribution. But if I were to approximate, if I were to like take 3 different simple distributions, 3 Gaussians per se, right? And if I were to take a weighted combination of these 3 Gaussians, then depending upon what weight I choose, I can sort of approximate this complex distribution. That's sort of the intuition, right? So you want to model something complex, you take something simple but take a mixture over them that adds expressivity to your model, right? And these individual components of your mixture are typically something simple like a Gaussian. All right, so that brings you to that gives you the idea of probabilistic circuit. It's basically having simple leaf distributions, and you have some product operators that takes products of your distributions encoding independencies, and you have sums that takes mixture and adds expressivity to your model. Now, how do you build a probabilistic circuit? Well, you stack these nodes as a computational graph, and you evaluate it bottom up, and the output of this entire graph, you would typically have one root node. This would be a rooted graph, right? So the output of your root node would give you what the density is, or the likelihood is, associated with each with the joint assignment of values, right? But this is not the complete picture, right? So simply stacking these models is not sufficient, right? If you just stack them arbitrarily, you cannot ensure that you can perform inference tractably over these models. So you need some additional structure here as well. So just like how you had like tree structure in Bayesian networks that enable tractability for marginal inference, we need to come up with some notion of structure in these models as well that makes the different probabilistic reasoning tasks tractable, right? Okay, so before that, so what do you think are the parameters in this model? Like, so this is just a representation, right? When I want to learn these models from data, I would be like learning some parameters which would ensure that the distribution models is as close as possible to your real distribution, right? So when it comes to probabilistic circuits, the parameters are obviously the weights that are associated with the sum nodes, right? Just like how you have weights in a neural model, this is a computational graph with weights, and you'll be learning these weights. Plus, you will also have parameters associated with the leaf nodes. So at the leaf level, if you assume something like a Gaussian, you have 2 parameters. You have to learn the mean and the variance, right? So those would be the parameters at the leaf nodes, and the internal parameters are the weights of your sum nodes, right? So these are things that you learn from data. Now, how do you learn them? We'll come to that. But I hope you get a high-level picture of how you represent what is a representation look like for these circuits. Yeah. One. Yeah, when you evaluate them, this is from bottom to top, right? But I just put the arrows showing how the joint distribution sort of decomposes. But the arrows are not really important because these arrows are not representative of any independencies, right? Unlike your Bayesian networks, this is a computational graph. Right? So the nodes here, internal nodes here, do not have any semantic understanding or relation with your random variables themselves, right? The only place where you'll be plugging in your variables are the leaves, and then you are just basically doing some computations. You're taking sums and products, right? So yeah, good question.
The x1, x2, these variables, do they correspond to the features in the data?
Right. So for each feature that you have a random variable, right? But you can have multiple distributions for each random variable. So for x1, you can like come up with 5 different distributions with their own parameters, and then you can combine them, right? So at the leaf level, you will have so like here, so the leaves, the scope of the leaves would be the variables x1, x2, x3, x4, but then you can have multiple distributions for each random variable. So here you have 2 distributions for x3, 2 distributions for x4, 2 distributions for x2, and 2 distributions for x1, right? And that's something you can vary, and the more distributions you have, the better you'll be able to fit the distribution, the joint, the real data. Yeah.
So, how, I just want to compare it with Gaussian mixture model. So, what is the
Right.
difference between
This is okay. A very good question, right? So if you think of a Gaussian mixture, so the probabilistic circuit is basically a more complex and cool way of putting a deep hierarchical Gaussian mixture model, right? That's the way I would put it. But the interesting thing is, unlike a shallow mixture model, shallow Gaussian mixture, what a probabilistic circuit does is it can encode an exponential number of mixture components in a very compact form, right? So this is, at the end of the day, it's a mixture model, like you said, right? But the cool thing is, so and mixture models, okay, let me talk about this, right? Why do you need mixtures? So if you look at generative modeling, you know that in the context of neural models are what are called universal function approximators, right? Similarly, in the generative modeling view, mixture models are, especially Gaussian mixture models, right? They are universal density approximators. So you can approximate arbitrarily complex probability density functions using mixtures themselves. That's like a classical result. But the issue is that you will need an infinite number of components in your mixture to fit any data distribution accurately, right? So if you have enough number of components, if you have like an exponential number of components in your mixture, then they are expressive enough. They might be a good model to fit any complex distribution. But then representing an exponential mixture is hard, right? You cannot just have a shallow mixture with exponential number of components. It just blows up, right? So how do you come up with a representation that is in essence equivalent to having an exponential mixture without actually having to do computations in exponential time? That's where probabilistic circuits comes in. So this representation, once you have this representation, so what you can actually prove is that for any probabilistic circuit, it is a mixture model that is exponential in the depth, right? So as you increase the depth, it's equivalent to having a mixture model with, say, so if you have a product node with 2 children, so you will have 2 power d mixtures. If you have, so for each probabilistic circuit, it has that expressive power, right, of encoding an exponential number of mixtures. But once you have this representation, none of your computations will take exponential time. It will only take linear time in your model, right? That's the difference. Yeah, but good question. Yeah.
Are we learning structures but parameters?
Good question, right? We'll come to learning. So you can learn structure as well. So there are 2 things that you can learn, right? The structure and the parameters. Is structure learning important? It is. Is it always useful? Might not be, right? So we'll come to learning in a bit, and what we'll see is that, okay, I'll talk about structure learning when we reach there. I don't want to jump the gun. Okay. All right. Any more questions?
Yes.
Please.
Here the assumption of the leaf node distributions being independent,
Mm-hmm.
so that you can take a product of them.
Mm-hmm.
So what is the implication of that assumption?
Right. So not all the leaf nodes are independent. So the thing is, so when I have a product node, their children should be independent, right? That's all I'm saying, right? But when you have a sum node that takes a mixture of 2 other distributions, that sum node sort of brings in a dependency between those 2 variables. Right? So even though you are encoding factorizations using a sum node, which will affect the expressivity, definitely, that's your question, right? What are the implications? So the implications of having product nodes and factorizations is definitely that your model will lose expressivity, right? But then to compensate for that loss in expressivity, you have the mixtures and sum nodes that will sort of bring in the dependence between those features and balance things. That's the intuition. Yeah.
The question is, when you're training the model, especially if you want to impose structure to it,
Mm-hmm.
what is the level of domain knowledge and domain
Mm-hmm.
thing that are used to give it a structure?
Okay, so when I talk of structure, there is the structure of the graph itself, and then there are additional structural properties that you need to ensure on the internal nodes themselves. From what I understand, you are asking what domain knowledge do you use to come up with the structure of this graph itself in the first place, right? So the thing is, most structural learning algorithms for like PCs, they are heuristics based, right? So you have some notion of scoring these structures, and then you use something like hill climbing search methods to come up with structure, right? You could incorporate domain knowledge into the learning if you have those. That is one of the research directions we work on in the lab, right? How do you incorporate domain knowledge into both structure as well as parameter learning, right? But as such, you do not have an interpretation like conditional independencies you have in Bayesian networks here, right? Because the internal nodes, they do not have explicit semantic association with any features, right? So it is hard in that case, in that sense. But what you will see is that you don't really need a lot of domain knowledge to build these structures. What you can really come up with is an ensemble of random structures, and they work beautifully well. That's what we will get at eventually, right? You don't really need structure learning, but structure learning can be useful as well, right?
Because we are looking at probabilistic reasoning at the end of the day.
Right.
So if
Right.
domain.
Right. So probabilistic reasoning in terms of answering the probabilistic queries, right? But identifying what independencies exist in this model is also a research problem. So querying this model to come up with what are the independencies encoded in this mixture model, right? That is also a research problem. So people have been looking at, like, how you can extract independencies from these themselves. Yeah. All right. Good. Yeah, please.
How is this different from some product networks?
So this is exactly a sum product network, right? So a sum product. So if you look at the literature, initially it started with from the logical side of things, right? So when you had you had logical reasoning tasks, you had first order, you had sentences in first order logic. There was this entire effort of compiling these into what can be computed efficiently, and that's where things like arithmetic circuits and stuff first came into being, right? Where so from a logical side of things, you can think of an OR node as an OR gate and a product node as an AND gate, right? And so the way it started was from logic, right? You compile logical sentences into these circuits, and eventually people started looking at, okay, what if I make this logic soft? What if I say that it's not always true, it's true with some probability? That is where these models, a probabilistic perspective started coming in, right? And the term probabilistic circuits was only coined in like 2020 by Guy van den Broek and his group. But even before that, what they were called were like sum product networks, right? But sum product networks is, you can think of them as a specific instantiation of this model where you have some structure defined over these product nodes, which are called decomposability, right? We'll come to those structure. But then these classes of models are more generic, right? So when you have appropriate other properties, you can think of them as other models, like say cut-set networks can be encoded as a probabilistic circuits. You can have Bayesian networks compiled into probabilistic circuits. So things like that. So it's more like a language. It's an umbrella term that you use for all these classes of models, which also includes some product networks. Right? Okay. So should we take a break or should we continue? Do you think? Is tea ready? Okay. Okay, we started 10 minutes late, right? So can we come back in like 10 minutes? Is 10 minutes good, or you guys need more time? 10, 15? Okay. Okay, 15 is fine. All right, so we'll start at like 10:37. How's it going? Remove this. Just don't want to go too fast. Okay, good. So where we stopped at was we started with the basic building blocks of a probabilistic circuits, right? What are they? You have the leaf distribution, sum nodes, and product nodes, and we sort of formulated that a probabilistic circuit is just these nodes stacked together in the form of a computational graph, right? But just stacking them together as a computational graph is not sufficient to ensure that your inference becomes tractable. You need to enforce some more structure over these graphs and internal nodes, right? So what are those structures? What are those structural properties that you need to ensure that inference becomes tractable? So we will look at.
Can I interrupt? Sorry.
Yeah.
It's the counter question.
Yes.
Go back one slide.
Okay.
So you said no, you need some structure. Why?
To ensure
Give
that.
me an example where just stacking arbitrarily is not going to be tractable.
Right. That's a good thing. Right.
Thank you.
Okay. So let's say I'm just coming up with a product node, right? What does a product node do? It's so like we said, products of distributions encode what? Independencies, right? So let's say I have say P1, P of x1, right? P of x, another distribution over say x1, or say let me take the case where I have three variables, right? x1, x2, x3, and I have a distribution, say, since we are looking at simple distributions, right, and I have multiple distributions, let's say P of x1, Q of x1, P of x2, yeah, just two variables. If I were to put a product node in this graphs arbitrarily anywhere, then you would result in some contradictions, right? So if I were to put a product node here, which is between x1 and x2, it is okay because x1 and x2 are two different random variables. They can be independent. But if I were to put a product node here, which is a distribution over x1 and another distribution over x1, that's sort of contradicting your notions from probability, right? Because they are both the same variables. They are distributions over the same variables. X1 cannot be independent of itself, right? So things like that. So if you have two sets of variables, right, which are overlapping, right, then they cannot be independent of itself, right? So you cannot just arbitrarily put a product node or anywhere in this circuit, right? You need to ensure that these independencies are like it's possible to satisfy the independencies they encode, right? So that's what we will look at. So to ensure that your graph encodes a valid probability distribution, you need some properties to be defined over them. We will look at three specific properties. The first one is called smoothness. The second one is called decomposability, and the third one is called determinism. Let's look at each of these, right? Now the smoothness. So you have internal nodes in a PC, which are in a probabilistic circuit, which are sum nodes and product nodes, right? So the structural properties we will be defining are with respect to these internal nodes, right? So smoothness, what does smoothness say? Smoothness is defined with respect to a sum node in your circuit, and you can say that a sum node is smooth if all of its children have the same scope. Now, what do I mean by scope? The scope of any node in your PC, or so when I say PC, it's basically a probabilistic circuit. Okay, so what does the scope refer to? So if you look at each internal node in this whole computational graph, it is computing a function over some input variables, right? So if you just roll out these computations, the output here would be in terms of some input variables, right? And the scope of a node is really the set of variables over which it is computing a function over, right? What variables are involved in that particular function at each internal node. That is what you call as a scope, right? Now you call a sum node to be smooth if all of its children have the same scope. So for example, if I have a distribution over x1 and say another distribution over x1, they are over the same scope, that is x1, right? Now I can define a sum node over them, and that would be a smooth sum node. But if they were over two different variables, then you say that the scope of this sum node is different, right? Which means in this case the sum node is not smooth. Now why do you need smoothness, right? And you say that a PC is smooth if all of the sum nodes in the circuit is smooth. Now the reason you need smoothness is because to ensure that you have valid mixtures. Now when you take mixture distributions, you're basically mixing simpler probability distributions, right? So to ensure that the output of a mixture is a valid distribution in itself, the individual components should also be defined over the same space, right? Otherwise it makes no sense to combine. You're combining two things, but they are not distributions over the same space, right? Which means you wouldn't get a valid distribution as the output. So our motivation behind these properties is to ensure that at each level in your probabilistic circuit, at each level in your graph, the computations transform your input distributions into a valid distribution at each step. You need to ensure that it's always a valid probability distribution, which is where smoothness comes in, right? So smoothness ensures that the output of a sum node is a valid distribution, right? So if I look, okay, so now so when you have smoothness, that is all you need to ensure that you can compute evidential inference tractably. Now why is that? So let's revisit evidential inference. What are we interested in doing in evidential inference? We are interested in computing the likelihood associated with a complete assignment of values to all your variables, right? So you're given an assignment, and now let's say I have a PC that models the joint distribution. How do I get the likelihood of a complete assignment from my PC. How does it look like, right? What does evidential inference look like when you have a PC representing this distribution, right? Well, I told you that what a PC does is it models the joint distribution as transformations of simple distributions, and the output of a PC is the joint density, right? Now, as long as you ensure that the individual components inside your computational graph maintain the validity of your probability distribution, that is, you get a valid distribution as the intermediate outputs in your PC, then you will have a valid distribution at the output root node as well, right? So all you need to ensure that you can compute evidential inference tractably for a PC is to ensure that your sum nodes are smooth. So let's say how this works. Let's see how you do evidential inference when you have a PC. All it boils down to is evaluating this computational graph, right? So how do you do that? So let's say I'm given values for my variables, that GDM is equal to 1, age is equal to 35, BMI equals 25, and I have a history of diabetes, right? And let's just assume that the weights currently are like something like uniform. You have some random weights associated with your sum nodes. Now, what does evidential inference look like? Well, I just plug in the values, right? So at the leaf node, I plug in the values for my variables, which are, let's say, so I plug in the values here at each of my leaf nodes. What do I get when I plug in the values at the leaf level? What do I get at the leaf nodes? I get the corresponding probability, right? So you get the corresponding probability mass or densities associated with those leaf variables. So you have some values at your leaf level, right? Now what do? You evaluate this graph bottom up, right? So it's just a computational graph. So when you have a product node, you compute a product of the values of its children. When you have a sum node, you compute the weighted sum of the values at its children, right? So it's just propagating these values bottom up, doing the appropriate computations. Now when you do that, you do this recursively until you reach the root node, and the output of your root node would be the joint density, right? The probability mass corresponding to the complete assignment of values to your variables. Is that clear? That's basically what evidential inference boils down to. In a PC, it's just evaluating the model bottom up, right? So this is given a complete assignment of values. Now let's look at the next type of inference queries that we discussed, which is marginal inference. Yeah.
Multiple structures giving the same answer.
Right. Yeah, we haven't talked about learning yet. How do you learn, or like, do you have a unique parameterization for each distribution and things like that? What I'm really just trying to convey is, given this representation, how do you do inference over this? What does inference boils down to? So I'm assuming that you're given the parameters. I'm not looking at how good the parameters are or how well it approximates the distribution, because that is something you learn from data, right? But the idea is, how do you do inference over this representation? Right? Yeah.
But maybe if I can answer, yesterday, even in the Bayesian network, I showed you the alarm network, and then I showed you another network, which exactly had the same joint distribution. So technically, it is just a factorization of the joint distribution. You could have multiple factorizations, and maybe the current data set can satisfy certain independence assumptions. That may not be true, in the grand scheme of things. But the small data set that you have might actually have incorrect independence assumptions satisfied, right? So the point being that yes, it is possible. I think his answer is that we will get to that. I would probably say, yeah, you could have it.
Yeah.
It's just
Right.
like you can have two deep networks give you exactly the same performance.
Right.
And so it's always possible.
Right. Yep. Yeah.
I think it's a point which smoothness ensures EDI to be tractable, right? So if smoothness is not, is not there, like say the nodes which are being summed are having different scope, then they can't be summed, right? It can't move forward.
I mean, from a computational graph perspective, you just have some values that you're propagating, but those values are not meaningful. Right? That's what you're saying. So yeah, so exactly. So when I say tractable, I'm talking of tractability for exact inference, right? So whatever values you get would be exact. In the case where it's not smooth, you're not having a valid probability distribution, which means your answers are not exact, right? So you're right. So if they are not smooth, you can still do some computations, but those computations and the answers you compute won't be meaningful. They won't be with respect to your the distribution that you're modeling, right? Any more questions? Yeah.
So the weights here, right? So if
If you are learning, yeah, when you are learning,
So it is okay. Yeah.
right.
So
Right, so you learn the models, right? This is, I'm just talking of how you do inference, given that you have the weights, right? But the weights are learned from data. Yeah. Okay. Yeah.
Yeah, the root node is always a sum node, right?
The root node is always a sum node.
So how will I ensure smoothness there? Because all the variables contribute indirectly to the.
Right. So the children of the root nodes, if you have a root node, let me go back to this. So let's say you have 3 children at the root level, right? Now each of them would be computing a function over the entire scope, right? So at the root level, you would be looking at all the variables. So if you have x1 up till xn, you have x1 up till xn as the scope of each children, right? So yeah, so at the root node, you will be mixing over the entire space, right? And at lower levels, you will be mixing over subspaces. That's the idea.
Like in the example of smoothness, when you're defining smoothness, you said for a sum node, both the inputs are at x1
Mm-hmm.
in your example.
Mm-hmm.
But here, indirectly, all the variables contribute. So will there be a scope here?
No, so I said the scope should be the same, right? Now, what does it mean by, so what is the scope? It is the set of variables over which the sum node, the node computes the function over, right? So at the root level, if this particular child here is a function over say f of x1 up till xn, and this is also a function some g over x1 up till xn, they have the same scope, right? So it is smooth. Is it clear? Okay. Okay, move forward. All right, so let's come to marginal inference, right? So we saw that when you're interested in doing marginal inference, which comes into play when you have missing variables, or you're interested when you're not given details of the entire states, the values of each variable that you're modeling, right? You need to do marginal inference. And what marginal inference boils down to, in the case where you have discrete variables, is performing summations over your joint density, right? And if you're marginalizing out a continuous variable, you would be integrating out all the values, right? So if you have a continuous variable here, let's say x is a continuous variable, then instead of the summation, you will be integrating out all the values that x takes, right? So what you really need to ensure is that, okay, if I were to perform an integration over the root node of my PC, can I perform this integration tractably in like linear time or something, in poly time basically, right? So to ensure that, we need a property called decomposability, and this is something that, you know, in the example that I mentioned earlier about not stacking nodes arbitrarily, right? So what decomposability basically says is that when you have a product node, it is encoding in dependencies, right? Which means when you have two subsets of variables as the children of a product node, those subsets cannot be dependent themselves, right? So you need those subsets of variables to be disjoint. So if you have a product node here in the first example, you have x1 as the scope of this first child, x2 as the scope of the second child. They are disjoint, right? Which means this product node is decomposable. In the case where you have overlapping sets of variables, so let's take a more different example. Let me say I have x1, x2, x3, x2, right? So this particular node is computing a function over these variables, and if I have a product node here, now I have an overlap between x2 in both, right? So in such a case, the distribution or the independencies computed by the product is not valid, right? So to ensure that, you need, so this property is called decomposability, which says that all product nodes in your probabilistic circuit should be defined over children having disjoint scope. Is that clear? Okay. All right, so now let's look at how, okay, when you have decomposability, you can show that marginals and conditionals can be computed in linear time. Now, why is that the case? So I mentioned that when you're computing marginals, let's consider the continuous case, right? The discrete case is even more simpler. So you have a probability density function P, which can be represented by a probabilistic circuit in our case, and we are interested in integrating out this particular probability value over the entire support of x, right? Now let's look at how this boils down to when you have a PC. So the nodes in a PC can be sum nodes or product nodes, right? When you have a smooth sum node and you're computing an integral over a weighted linear combination, right? let's say you have P1 and P2 as the children to the sum node, and you're computing an integral over the output of your sum node, you can basically decompose this integral and write it down as integrals defined over the children themselves, right? Because it's just coming from the linearity there, right? So you can take the weights outside, you can push the integrals down into the children, and you can just basically compute the integrals over the children and then take a sum over the integrals, right? So that's more of pushing down the integral from a node to its children. Now, intuitively, if you think of this, like if I can somehow do this recursively until I reach the leaves, right? And the leaves, you have simple tractable distributions. Those integrals over those simple distributions can be analytically computed, right? And if that's what it boils down to, then I can just plug in those values, and this entire integral becomes very simple to compute, right? That's where we will get it. Now, you cannot do the same if you do not have a decomposable product node, right? But if you have a decomposable product node in your circuit, which means the scope of these two children are disjoint, then you can write the probability over the joint probability as the product of your individual probabilities, and you can also push down the integral into the children, right? So this is it's very simple, right? So you have P1 to be independent of x2, so you can take integral over P1 x1 outside and the integral over P2 x2 as something separate, right? And what you can write down the joint integral as a product of integrals defined over the children, right? So you're again pushing down the integral defined over a node to its children, right? Is that clear? Yeah. All right. Now,
Just want to point out one thing. I think one of you asked the question yesterday about discrete versus continuous, and you can see the variation. Yesterday, every example was discrete. Here, most examples are continuous because, I mean, that's the versatility of these systems. I just want you to kind of get that particular aspect. Mixed data types are actually very easy to handle.
right. And just to point out like the intractability here, right? So when you have a continuous space, ideally, if you cannot do this pushing down and you have some model that is representing P of x, right? And you're interested in integrating out the values of P of x across the entire support of x, why is it infeasible? Because you have an infinite number of values to integrate out, right? There's no direct way to do this integral. And what we are trying to do is to come up with a way that makes this very easy to compute. And the idea that we are looking at is to decompose this integral into something simpler, right? So if you have smooth and decomposable nodes in your PC, and let's say we are starting with a joint distribution over 4 variables, and we are interested in marginalizing out, say, the variable x1, right? So how would you start doing this? So I know that the output of my root node gives the joint density. Let me define the integral over the root node. But if you have a smooth sum node, I can push this integral down. So what it boils down to is so the integral now becomes over the product node, right? And if you have a decomposable product node, we saw in the previous slide that you can again push it down to the children of the product node, right? So the integral basically decomposes to the leaf here. So you can keep on pushing this integral from a node to its children until you reach the leaves. And at the leaves, you have simple univariate leaf distributions, right? And if you're integrating out the values of the distribution across its entire support, what do you get? If you have a distribution and you're summing over all the possible values of your probability, or if you're integrating out all the density, you get 1, right? Because that comes from probability theory, right? That is the definition of a probability distribution, right? So what this boils down to is plugging in the value 1 at the leaves that you're marginalizing out. And so you can see that when you're interested in marginalizing a variable, and this is applicable to any set of variables that you're marginalizing. So in this case, I just showed it for 1. It's also the case when you're marginalizing out any combination of these features, right? All you have to do is replace the features that you're marginalizing with 1, right? And then do the computations bottom up. So if you were to evaluate this circuit in which you have replaced the values of P of x1 with 1, then what the network would be evaluating is the marginal distribution. Is that clear? How we came to that? Yeah. Not necessarily, right? What you're only saying is that, so for this pushing down to happen, we did not assume independence between x1 or x2. All we looked at was the properties of a product node. If the product node has disjoint scope, then you can push this integral down. But there is dependence between the variables coming in from the sum node. Right? The sum node makes different sets of variables dependent, but when you're computing the integral, that dependence doesn't really matter. You can still push down those integrals because of the linearity of your weighted combination. Right? Okay, so that's marginalization, right? So you can, so how much time does it take to do marginal inference over PC? It's basically a bottom-up pass, right? So it's linear time in the size of your model. Now, if we come to the third class of queries, which are conditional inference queries, in which you are saying you're interested in computing the likelihood of, say, P of A given B, where you're given a set of values that you have already observed for some variables, and you're interested in reasoning about the likelihood over the remaining variables. So, like the example we saw, what is the likelihood that a pregnant woman has gestational diabetes, given that she is 35 years old, has a BMI of 25, etc. Right? Now, if you apply Bayes' rule and you write this query down, what you can observe is that the conditional query boils down to two things, right? So, what is the numerator here? If I were to think of the queries that we have discussed so far, evidential inference. So, this is evidential inference. What is the denominator? You are doing a marginal inference, exactly, right? And we saw that if you have smooth and decomposable PCs, evidential inference is linear time, marginal inference is also linear time, which means conditional inference is also linear time, right? So let's make this more formal. If you're interested in, say, if you're interested in looking at the conditional over x2, x3, x4, given x1, this is what the Bayes rule gives you, right? Now we know that you can compute the joint density just by a bottom-up evaluation, right? And we know how to do marginal inference. How do you do marginal inference? Well, you take the same circuit, you set the variables that you are interested in marginalizing out to 1 and evaluate it, right? So so you basically make 2 for bottom-up passes, which means it's still linear time. You only need 2 bottom-up evaluations. So conditional inference is also tractable for PC, right? So I think someone was asking, how does like inference become tractable, or how do you prove inference becomes tractable, right? So I hope you have your answer now, right? So you say that whatever operations is involved with these queries can be computed in polynomial time, right? Under appropriate properties. That's the argument that you follow. All right, so now let's look at the fourth query, which is a bit more complex. What you're saying is that, okay, you're looking at what values of random variables maximizes your joint density. Right, so you're interested in performing an argmax operation defined over your joint probability mass function or density function. So in this case, you're asking what age group and BMI of women having family history of diabetes is most likely to develop gestational diabetes, right? So you know that GDM is 1, history is 1, and you are interested in finding the argmax over age and BMI that maximizes this particular density. Now, well, you know that this is a conditional query. This is a conditional query, right? But this is proportional to, okay, what is P of A given B? It's P of A comma B by P of B, right? And we are interested in maximizing age and BMI, which, so if you write this down, you are not really interested in looking at the denominator, right? So this, if I were to expand, it would be P of age, BMI, GDM, and history divided by, what's the denominator? It would be GDM and history, right? Now, when I'm doing a argmax over age and BMI, this denominator doesn't really matter, right? Because it doesn't have age or BMI. So what I need to do is just maximize the joint density here, right? But it's not as straightforward as we did before, because doing a maximization operation is different from doing an integral operation, right? But the line that we were following in making things tractable was in somehow pushing down a complex thing into something simpler, right? So if you want to do an operation at a higher level in your circuit, and if you can push that down, decompose it into something simpler defined over its children, then it can be done in linear time. That's sort of the argument we were following, right? Now let's see if we can do the same thing for maximization operation, which is involved with map inference. Right? So if you have a decomposable product node, right, then, and you're interested in, say, maximizing over x1 and x2, then since if this is decomposable and their scopes are disjoint, right? Then this is it basically boils down to max over p of x1 and max over p of x2. Right? That's straightforward, right? So if you have a max operation over a decomposable product node, you can write it as a product of max over the children of your product nodes, right? So okay, you would think, okay, then it should be tractable, right? You can still do just map over your leaf and then propagate the max values bottom up, and that should give you the answer for your map. But unfortunately, the sum node creates an issue here. Why is that? Because when you're taking a sum, you're doing a convex combination, and the maximizer over a convex combination of inputs is not necessarily the convex combination of individual component maximizers, right? So does that make sense? So if you're taking a convex combination of say k entities, say w1 p1 of x plus w2 p2 of x, so the maximizer for this is not the maximizer of these individual p1 and p2 taken a convex sum, right? So you need some additional so you cannot push down the max from a sum node to its children, right? So again, if you look back, so things become intractable here, right? So what do we need to do when things become intractable? We need to define more properties, right? So we need to define additional structural properties for your sum nodes to make map tractable. Okay, and that property is called determinism. Now what a determinism says is that you consider a sum node. You say that a sum node is deterministic if the output of its children is non-zero for at most one of its children, right? So if you have a sum node and you have inputs to your sum node, and you ensure that at most one, right, at most one of these children is non-zero for any input, then you call that particular sum node to be deterministic. Now what does this look like, right? So if what do sum nodes model? They are like mixtures, right? They're convex combinations of distributions, and if they are smooth, they are defined over the same space. Now the way I would try to explain or like give you an intuition as to how this looks like is, think of the support for your distribution. What does support mean for a distribution? Support is the range of values for your variables over which the probability is non-zero, right? So if you have a distribution like this, right, so this region is the support. For the remaining region, your probability is 0, right? So you consider, so for a sum node, you look at its children, the distributions corresponding to the children of the sum node, right? And if they are overlapping, right? So let's say in this case you have some overlap here. So for any data point here, the output of both of these children would be non-zero, right? Which means it is not deterministic. But in this case, let's say outside the colored regions, the probability is 0 for each child node, right? So in this case, you have you have disjoint support, which means for any given region, for any given input, at most one of these children would be non-zero. Does that make sense? Is that clear from this? Why this is deterministic? Yeah, sure. So determinism, what does determinism say? It says that if you consider all the children of any sum node, right, at most one of them can be non-zero, right? So it should, so if this one is positive, non-zero, then the other two should be 0, right? And the way I try to explain this is, think of a mixture model, right? Because what sum node does at the end of the day is taking a mixture, right? But think of a mixture that has disjoint support. It's more like partitioning the space, right? Let's say you have a partition like this. You have a mixture 1 here, mixture 2 here, mixture 3 here. In this case, for regions outside this particular triangle, the probability for this mixture is 0. So something like that, right? So you have 3 children here. You have the support for each of these 3 children, but they are not overlapping in any way, right? So, and in this case, you have regions in which these models overlap. So for any data point that belongs to the intersection of these regions, say here or here, then multiple nodes would be non-zero. They would be outputting a probability that is non-zero, right? Because it is included in its support. In which case, this is not a deterministic sum node. But here, since it ensures that the output is 0 everywhere outside the circle, and there is no way it can intersect with any of the other circle. So for any given data point, at most one of these nodes would be non-zero. Does that make sense? So this is a deterministic sum node. Yeah.
So yeah,
Yep.
decision trees here.
Yeah, that's what you have here.
The mixtures that he drew, that one that he has, are just arbitrary mixtures. If they were axis parallel rectangles, essentially you get a decision tree.
Right.
Right? Decision trees are great because they have this one property. It's called single path semantics, which means for any given data point, you are guaranteed to go through only one path. Okay, so that is an example of a deterministic mixture. Okay, a decision tree is a deterministic mixture. For any point, you are guaranteed that you are only in one path. Every other path is false for that data point.
Right.
The same property extended to a sum node is a deterministic property.
Right.
It's a single path semantics. Right?
Yep.
But there is one key difference. I'm sorry.
Yeah.
In a single path semantics, you have to have one path that is satisfied. Here it is at most one path, which means none of them could be satisfied as well. And that is okay. So that's the key difference. So for me, decision trees are a special case of this deterministic sum node property.
Right. Right. And that is one of the way how you make a sum product network or a probabilistic circuit deterministic. You have things like a rule here, right? So you sort of just like how he said, you have decision rules. So at a sum node, if let's say it's looking at the variable x1, and I look at the support of x1 and say if x1 is less than 1.5, then I evaluate this particular node. Otherwise, I take this particular path, right? So it's more like multiplying this with another Boolean variable that triggers only when this condition is true, right? So you can think of so associated with each path, you have a set of decisions that you're taking, right? And those decisions would definitely be disjoint because you can only take one path. X1 cannot be both less than 1.5 and greater than 1.5, right? Makes sense? All right. Yeah.
How do we enforce this as a constraint on the parameters?
Right. So one thing you could do is it's not a constraint over the parameters. An easy way to do this would be, so let's say I have a sum node.
Could you maybe,
Yeah.
while you are trying to draw that, it's not really a constraint over the parameters, it's a constraint over partition function.
Right.
So for me, that is the easiest way I implement. But these guys are coding, so they'll have a better.
Yeah, I was just saying the way you would implement it, exactly like he said, right? Now, this is a sum product network, so you have, say, a distribution here, right? And you want to ensure that this distribution, the output of this node is non-zero only when this condition is satisfied. Well, what do? You just take a product with, you take the product with another node, which is, you can think of it as a Boolean variable that is 0 if this condition is violated and 1 if this condition is satisfied, right? That's all you need to do, right? That ensures that the output would be always 0 whenever the condition is not satisfied. Yeah. All right. So, sorry.
You said there need not be a path, right? It is not. So when we split the range, so here you are partitioning the range of the random variable. So for a particular range, there need not be a.
I mean, the density there could be 0. Completely, it could be 0. Whereas in a decision tree, you have to take a path. So to me, a decision tree is a special case of this deterministic sum node. R trees are examples. Those can do that. So
That is why the utmost, so it's like
Yeah.
0 at that range.
there has to be no more than one node with non-zero, probably, right? That's the thing here.
Yeah.
But in decision tree, it has to be exactly 1. That is the difference.
Yeah.
This is no more than 1. There, it's exactly 1. That's the difference.
Yeah. Yeah.
We learn these values
That will come to. Learning is still not done.
Yeah. We haven't reached learning yet, but we'll come to that.
Definitely come.
All right. So, any more questions? Okay. Okay. So how does map become tractable when you have determinism? Let's look at this the operator that we're doing, right? When you have a deterministic sum node and we are interested in doing map, what are we doing? We are taking a max operator over its output, right? Now we know that if you have a deterministic sum node, only one of its inputs would be non-zero, right? So if you were to take a sum over these children and you already know that only one of them would be non-zero, then that is equivalent to taking the max over the children, Is that clear? Right? You have a summation wi pi of x, right? But you know that only one of pi is non-zero. So taking the summation is actually equivalent to taking the max over all of your pi, right? Right? So you can push down the max operator from a sum node to its children if you have determinism, right? All right, so let's see how this actually works in practice. So you want to compute maximization over the joint probability density. If your model is decomposable, that is associated with your product nodes, you can push down the max operator from your product node to its children. If it's deterministic, you can push it down from the sum nodes to its children, right? So what do you do to push down the max operator from the sum node to its children? You replace the sum with a max operator, right? So what you really need to do now is to evaluate this, what you call a max circuit, where instead of sum, you're doing a maximization at the sum nodes, right? And when you recursively push down this max operators from a node to its children, you end up with maximizers defined over leaf distributions. And your leaf distributions were assumed to be tractable, right? Something like Gaussians. And what is the max doing? It's just computing the mode of that distribution, right? What is the density, what is the value that maximizes that probability distribution, which is the mode of that distribution. And since we assume it to be tractable, you can compute it. You know how to compute the modes of simple distribution. So what do? You just plug in the values for the modes for the variables that you are evaluating or like maximizing over at the leaves, right? So let's say we are interested in maximizing over everything, x1, x2, x3, x4, right? So you replace the values of all the leaf distributions with their modes, and you make the forward pass. And when you do this, what you really get, so we are interested in computing argmax, right? But so far we have been doing what? Max, right? So when you do this, what you will get is what is the maximum density associated. You won't still get what is the value that resulted in that density, right? So to get the value, all you need to do is simply keep track of which path you took. So let's start from here, right? So you're doing this maximization operation here, and you know that this is the node that resulted in the maximum, right? So you keep track of that path of the input, and then you continue doing this, right? When you continue doing this, you will end up with one distribution per random variable that you have, and the value that maximizes that corresponding leaf distributions would be the value that maximizes your joint, right? All right. So if you talk of computation time, how much time does it take? All it takes is one forward pass and one backward pass if you want to get the exact values of a random variable. So it's linear time, right? So you can compute map in linear time if you have decomposable and deterministic PCs. So just to put those everything in one slide, right? So we looked at 4 different query classes: probabilistic reasoning queries, evidential, marginals, conditionals, and map. And we came up with structural properties that resulted in tractability for each of these queries, right? All right. Now let's come to learning. So we haven't yet talked about how you learn these models, right? So just like how he was explaining yesterday, when you think of a model like a PC, there are 2 things, right? You have the parameters that are associated. What are the parameters that you learn in a PC? They are the weights of the sum nodes and the leaf distribution parameters, right? And the structure is basically the structure of your computational graph. Now structured learning is a hard problem, because if you want to do tractable inference for the queries you are interested in, you cannot have arbitrary structures, right? It's structured learning with constraints, because you want to ensure that the properties such as the decomposability, smoothness, determinism, etc., is satisfied by the structure that you are constructing, right? Now, when it comes to parameter learning, okay, so the approach you take to do parameter learning is obviously maximum likelihood, because you have a way of, when it comes to models like probabilistic circuits, you have a way of directly evaluating what the likelihood is associated with each input data point, right? And what is the best model that you can get? It is the model that best explains the data that you have, right? It gives the best likelihood for your data distribution, for the data that you have at hand. So you can do maximum likelihood training, in which you are interested in finding the parameters that maximizes the likelihood or the log likelihood. So the reason you use log likelihood instead of likelihood typically is when you have these computational graphs, right? and you're taking products over values, these values are actually very small. So when you have a huge distribution, your density values associated, let's say if you have like 20 features, right? You have a huge possible state space, right? And the probability values associated with each assignment could be very low. Now, when you're plugging in these low values to a circuit and taking products, right? Then they're already between 0 and 1, and they can be very small as well, right? So you can result in underflow in your computations. So to make things stable, you typically work in the log space, right? Where you compute log likelihoods instead of likelihoods themselves. So you maximize the log likelihood. Now, how do you maximize the log likelihood? Well, if your model is deterministic, then you have a closed form solution for MLE, because you have a fixed path that you take for each data point. Right? For each data point, what you would result in if you have determinism is in a single path in your PC, and you know that when you take that single path, at the end you have a tractable model, something like, say, a tree Bayesian network or Gaussian models, right? And when you have such tractable models, we saw yesterday that doing MLE reduces to just doing counts. You have some sufficient statistics, and you compute them by counting from the data that you have, right? So it requires only a single pass on your data set if you have determinism, right? But deterministic PCs are not always expressive. They are not as expressive as non-deterministic PCs. And the non-deterministic PCs are also a bit more popular when it comes to modeling more complex distributions, right? So how do you learn non-deterministic yet smooth and decomposable PCs? Well, if you think of what a PC does, it's basically a computational graph, right? What is your neural network? It's also a computational graph. And how do you learn a neural network? You do gradient descent, right? Is everyone familiar with gradient descent? You are interested in finding the local optima, maxima, or minima of a function. What do? You start from some point. You look at what is the direction of maximum change, maximum increase. You go in the reverse direction. You go in the direction of maximum decrease if you are interested in minimizing that particular function, right? And you keep this iterating. You iterate over this until you converge. That's what gradient descent does, right? Now, in PCs, you can do the same thing. What would be your loss function here? Your loss function would be the output of your root node. It is the log of the output of your root node. But this is computed with respect to, when you have a PC, it is a function of your weights, it is a function of your input distribution parameters, right? And this is an entirely connected computational graph, so you can differentiate the output with respect to the input, right? You can do that using backpropagation, and you can update the weights and learn the parameters using gradient descent. Now, so gradient descent is just one way of learning the parameters of a PC. People have also looked at other methods, right? And one other popular way is to do expectation maximization. EM is something we discussed yesterday, but the way we discussed EM yesterday was when you have missing data, right? Then you can compute what the expected values are for your missing variables, and then you can maximize it and then keep on iterating until your model converges. That was the idea, right? So the question you would have is, okay, what are the missing variables here if I were to do parameter learning, right? I do not see anything missing. Well, you can come up with an interpretation for your sum node. What does a sum node do? It is basically taking a mixture, right? So you can say that I have two components here. Each of this is modeling. So associated with each sum node, you can introduce a latent variable z, where z equals 1 corresponds to the first component, z equals 2 corresponds to the second component, right? And you can write down this computational graph in something similar. So you can say that the weights correspond to something that looks like the prior distribution over this latent variable, and the distribution computed by your children is nothing but the condition over x given that you take that particular path. Now, in this view, z here is something you do not know a priori, right? You do not know which path to take for any given data point. It's some latent information, which means if you think of a joint model where you have x and z, z is something like a missing information, right? So you can apply expectation maximization in this context to learn the parameters. That's like a very high level overview, but if you're really interested in how the EM is done and how you are materializing this latent variables, do check out this paper from Robert Pahas. All right.
Yesterday I did say that you can use CM in the context of hidden data, but really it's in the premise of latent information. And that could be data, it could be models, it could be anything. In my PhD thesis was on doing observe data with a latent combination function like he talked about, right? So it's about the fact that anywhere there is latent information, EM seems to be, it's natural. It's basically EM, to kind of fill in the missing patterns. Just want to make that clear. It's not necessarily missing data, it's latent information.
Right.
Do you want to give them like a minute break or something? Or just your call.
It's their call. We just have 30 minutes. We can go, I can cut down on content. We can discuss other things tomorrow if we cannot complete everything. But it's, do you guys want to take a break? Maybe 2 minutes break, I guess?
Yeah, why don't we take it?
Yeah.
So, what exactly do you mean by deterministic PCs and non-deterministic PCs?
So deterministic PCs are PCs which satisfy the structural property of determinism, right? So when it comes to, so one of the ways I said in which you can enforce determinism is having something like a decision tree, right, which ensures that for a sum node, at most one path is taken, right? So in such cases, so for each data point, you would be evaluating just one particular path, right? And the densities you would have is the densities coming in from the simple distribution that you have for that data point, right? And computing the parameters for that is just counting, right? So it's, it can be done in closed form when you have determinism. That's the point. Right, they cannot do MAP, but you can approximate MAP. You can still replace, do the same thing, replace some nodes with max, right? But that won't be exact map. It would be an approximation for map. Yeah. And there are like recent works that looks at other ways to approximate map, marginal map, etc., even without having very restrictive structural properties. So there's a recent AI stats paper from our own UTD group, Professor Vibhav's group, on computing marginal maps using a neural model, combining a neural model with a PC and stuff like that. So it's a very hot area if you're interested in working. Yeah. Yeah.
Expectations of maximization. It is understandable for the missing values, but here we are creating one dummy variable intentionally and then we are using
It's not a dummy variable intentionally. It's another view of viewing. So what are the parameters you want to learn in a PC is the weights associated with your sum nodes, right? Now, another way of viewing these weights is from a latent variable interpretation. It's another interpretation. So you can think of the weights W as a prior over some path you're taking, right? So if you're taking a particular, you have some importance given to a particular input for your sum node, right? That is more like a prior over that path. You have P of Z equals, let's say, I. Let's you're taking the first node, so you have some prior over how important that particular node is, right? And what the node models is how much that particular path can approximate the underlying distribution P of X, given that you have taken that path, right? This is just another interpretation for your weights, right? Now, in this interpretation, Z's are actually latent variables. They are hidden information, which means you can apply EM here. And what you would be learning is basically P of Z, which are the weights themselves again, right? Right. Good? Okay. Okay, so that was about parameter learning. Now, like one of the, like many of you asked, what do you do to learn the structure? What domain knowledge can you incorporate to learn the structure? Structure learning is a discrete optimization problem. It's a hard problem, I agree, right? And I do not have a solid answer as to what is the best way to do structured learning because it's an open research problem. But if you look at the literature, most structured learning algorithms, they are somehow heuristics based. So you come up with some heuristics to score the different structures that you're building, ensuring that they are valid structures, they satisfy determinism and decomposability, not determinism, smoothness and decomposability. And you score those, and then you decide if you want to grow this structure or prune the structure, whatnot, right? So in structured learning, how we saw yesterday, there were like different operators like adding an edge, reversing an edge, deleting an edge. So in a PC, it would be, you would be deciding whether you have to expand a node by adding more sum nodes, or prune an edge by deleting something, right? So there are different algorithms that look at this from different perspective, from a pruning perspective, starting from something fully connected and then pruning, or starting from something small and then building it up, right? And one of the most popular algorithms is the learn SPN algorithm that learns the structure from data via something that is called, that can be viewed as recursive slicing. So if I think of my entire data set, let's say it's like a fixed dimensional data set, I can think of it in terms of a huge table where across the columns I have my features and across the rows I have my individual data points, right? So at the root node, what do we have? We have a sum node. We are starting with a sum node at the root, and we are interested in building this PC top down. So what do you do? Well, what does a sum node do? It takes mixtures, right? And one way of getting good mixtures and defining how many, like what components do you need for a mixture, is doing something like clustering or the k-means algorithm, things like that, where you cluster your data table, or let me call this the data table. You cluster this based on the support across this, right? So you group instances based on some sort of similarity measure, and let's say you group them into 3 components where you have the first one corresponding to these entries, the second one corresponding to the orange entries, and things like that, right? So this is similar to what you would do in like clustering or k-means, right? And one easy way to get the weights here would be the number of data points that belong to each cluster themselves, right? The relative fraction. So this is again heuristics based, right? Since some nodes are similar to mixtures, you can cluster them to get child regions. And what do you do? So what you would typically see when you're building probabilistic circuits is that you have alternating sums and product nodes. Why is that? It's not really meaningful to have sum over sum, because it's as good as having a larger sum, right? And product with product is just as good as having a larger product, right? So you typically have sum nodes followed by product nodes and then sum nodes. So you keep alternating between sums and products to build this network, right? So once you have at level 1 the children of sum node, this is still over the entire set of variables, right? And you need a product node to decompose this into something smaller. Now, how do you define what sets of variables to decompose them into? Well, since product nodes encode factorizations, I can think of finding independent groups of variables. So if I have x1 up to x5, I can use some sort of independence tests to say that, okay, so for this particular node, I would only be looking at this subset of data, which is the blue colored data. And within that region, I will be looking, okay, which variables are independent, can be interpreted as independent of each other by running some independence tests, right? So let's say for this particular node, I have this green colored features and blue colored features to be independent from my independence tests. Then I can define a product node there where I have 2 children corresponding to these 2 subsets of variables, right? And you can keep on doing this, where at the sum node you again do clustering. So clustering is morely slicing your data table across like horizontally, and at a product node, what you're doing is running independence tests to slice the data table vertically, right? And this results, you can keep on doing this until you reach like at least a single feature at your leaf. Or you can have criterion that says, okay, if I have these many number of data points only at a sum node, I stop the splitting, and you have other heuristics like that, right? So this is one way to learn the structure in probabilistic circuits, but this is very commonly like used. Now the way we constructed this, the construction, like the structure learning by construction, it satisfies smoothness and decomposability. Why is that? Smoothness can be enforced. All it needs is to ensure that your variables have the same scope, or have the same support, sorry. And decomposability needs your variables to have disjoint scope, and we ensured that we were splitting the variables into disjoint partitions when we were running the independence test, right? So the way we are constructing this itself, by construction we are ensuring that these properties are always satisfied, right? So they are tractable for marginal and conditional inference. Okay, so that was just like a couple of algorithms that people have proposed for learning these. But there are other methods as well. You have for structure learning things like you can take a Bayesian view where, okay, I come up with a Bayesian score for my structure where I evaluate how good a structure is in terms of its contribution to my joint overall likelihood, right? So if I think of if I think of a joint over, I call the structure G, graph, and theta, and I have data set D, right? Then I can compute what is P of D given theta comma G, right? Now, from this joint distribution, from this distribution, if I can marginalize out over the entire parameters, then I effectively have a score that gives me how good is a particular graph structure, right? So people have looked at that perspective, which is a more principled way of doing structured learning, right? You come up with a probabilistic, you take a probabilistic view where you come up with a probabilistic score for the structure that you have, and then you use that in a search algorithm to get a structure. So that's some structured learning algorithms, and we have a recent survey paper that has been accepted to IJCAI where we have taken a look at the field entirely and sort of build a taxonomy of the different learning algorithms, both for parameter learning and structured learning, and also what other design extensions people have proposed in the literature to make these models more expressive and tractable. So if you're interested, definitely do take a look at this paper. We'll be covering some of the works mentioned here tomorrow, but I just wanted to like let you know that the works that we have covered is not an exhaustive view. It's just a couple of instances of the things that you can do, but there are a lot of other algorithms as well. All right, so okay, maybe I think we can what we can do is I can show you a demo of probabilistic circuits right now, and then I can start with how people have made these deep tomorrow. Maybe. All right. So is there a way I can connect my laptop? I was told there would be an HDMI cable somewhere. Or I could just, you guys can also open this from your laptop if you have it. .ly/pdgm-2. So I'll first walk you through, like just to give you a brief idea of how people have done this, like coded this. So there are different packages that are already available for implementing. Yes, sure. Let me. I have it on the slides. It's bit.ly/pdgm-1 and 2. Let me see where I have the slides. Yeah. This. Good. All right. So this is an implementation in PyTorch. So I mentioned that
Sorry, I'm going to interrupt you because I really want to make this point alone. So, 10 years back, I was standing not in this room, but in one of the other rooms, in the computer science department, teaching the same tutorial, but without the circuits aspect. There, the problem was the Bayesian network core never scaled. So we were not able to use any of the existing APIs, get it to run faster, maybe 12 years back, I forgot when. And so I had to use our own lab code to show something, and it never worked. One of the reasons I think there is a new resurgence in this field of probabilistic models, and particularly these tractable models, is how easily you can do this on top of PyTorch or any of these existing APIs that one can just do plug and play, right? So that's one of the reasons I think we are more excited about this tutorial. We've been doing this for now 1.5 years, often because of the fact that you can just plug and play at this point. So if you ask me why should I do this over Bayesian networks, this is the reason. Why I would like Bayesian networks is still because it's not deep, and that you can still use have more explainability compared to these methods. So that's the choice, design choice you make. So as somebody who's building these systems, we do both. We build, I mean, like Sahil has cited a few papers of his and Saurabh here, but Saurabh has a bunch of other papers on using knowledge to build Bayesian networks for clinical data. So all I'm saying is that it's horses for courses, particularly to the students. Do not decide the hammer before you see the nail. Find your problem and then figure out which hammer best fits the nail. Okay, so I just want to make that clear. But this is what I love about this tutorial is the fact that we can just plug it into existing code. Sorry, I didn't mean to steal
No,
your thunder.
you're
but I
good.
have to-
Thank you. All right. So I mentioned that the way you learn these models, you can implement them in libraries that support like backpropagation, right? Like PyTorch, TensorFlow, whatever you like, and then you can just train them using gradient descent, right? Just like how you would train a neural model. So this particular example here, that is what is called an Einstein network. It is an implementation of a PC in PyTorch. What exactly is the algorithmic innovation in Einstein networks as compared to other models? I will come to that in like tomorrow's talk. But today I just wanted to give you a view of how these models looks like when you are coding and maybe get you excited about some of the things that they can do so that you feel motivated to come tomorrow, right? All right, so we will basically be there's a GitHub repository for Einstein networks. It is built by Antonio Vergari and their group. So we'll be just cloning the repository and just using the models here, right? So when you have a generative model, you're interested in modeling a distribution, you need a data set, right? And a data set, I like image data sets even though professor doesn't, and I like the MNIST data set because it's easy to work with, right? And it's something nice. So we'll be using the MNIST data set here. All you have to do is, so they have an entire implementation for all the operations involved, the computational, how the computational graph is built and stuff. We'll be just importing the Einstein network from the repository, right? For this particular case, let's just consider 3 classes from your MNIST datasets, the digits 1, 2, and 3. What is the state space here when you have
When Jan LeCun gave a demo in 1989, he showed how well the US postal code could work with CNNs. You just enhanced it and have an MNIST data set that all of you are bringing over. So that's why I don't like it. It's not like I don't. Jan LeCun did it in 1989. And Jan LeCun is still doing it. That's a different point. But you should see that video. Now it's on Twitter everywhere. The really old Jan, I mean, the really young Jan LeCun, sitting in front of those 1989 computer, the monitor, and giving a demo of scanning a paper in which numbers were written, and the output comes on the monitor. So the modern version of that is MNIST. So the US Postal Service has been using automatic digit recognition for 25 years. So why am I excited about MNIST? I don't know. So you guys move the needle from 96.676 to 96.678 and publish a paper. And you want me to be excited.
I mean, people haven't done it with PCs yet, so right.
Again, that's just a new. It's the same nail. You're just having a new hammer.
Yeah, that's true.
But let's go.
I mean, I cannot have
Anyway,
cool
we'll fight over lunch.
visualizations. All right, thanks. Okay, so what are your random variables when it comes to images? What are the random variables for images? It's the pixels, right? So when you have a image of height 28 and 28, how many random variables do you have? 28 cross 28, right? So you have 784, right? Random variables. So these models, so the Einstein network, it's more like a deep model. So there are hyperparameters that you can fix. Things like what is the depth of this model, right? So if you think of depth in a PC, unlike a neural model where you can stack, say linear feed forward layers or CNN like convolutional layers arbitrarily, there is a limit to the possible depth that you can have in a PC. Why is that? Because at each product node, you are decomposing, you are sort of partitioning your variables into disjoint sets, right? And there is a limit to which this partition can be done. The moment you reach like one variable, you cannot partition it anymore, right? So there's a limit to the depth, which would be like a log of the total possible variables you have, right? So if you have k variables, your depth can be at most log k to the base 2 if you are decomposing it into 2 splits at each product node, right? But here you have 784 random variables, so you can have a large depth. Depth of 4 is still okay, not so big. Now there are other parameters associated with this model that governs the expressivity. So number of repetitions and k, they are basically looking at how many distributions are you gonna use for each leaf variable, right? So I mentioned that at the leaves you have distributions over single features, right? But you can have an arbitrary number of leaf distributions, different distributions over the same feature, which you are combining using products and sums, right? So by varying this k here and number of repetitions, you are allowing for more components in your mixture to be modeled for each variable, and that increases the expressivity of your model, right? It also increases the number of parameters. So what we will do is, okay, what else do you need to specify in a PC? You also need to specify what leaf distributions you are using, right? So here, when you have a pixel, you think of it as you can either think of it as a discrete variable or a categorical variable, depending upon how you view it, right? If you are normalizing it to the range between 0 and 1, the pixel values, then it's a continuous variable. But if you think of it as values between 0 to 255, then it's a discrete variable, right? So depending upon how you like pre-process your data set, you can either use a continuous distribution or a discrete distribution. So if you have a continuous distribution, I'll be using a normal distribution, a Gaussian at the leaves. If it is discrete, if my data is like discrete, then I'll be using a categorical distribution, right? The rest of the things, it's more like how you train a neural network. You define how many epochs you want to train it over, what batch size you're going to use, right? So you load the data set, you pre-process the data set. It's basically converting it into the range 0, 1. And I'm using a normal distribution. You create a training split, a validation split to evaluate how good the model is fitting my distribution, right? These are standard things you do in deep learning, right? All right, so now I am importing the model from the library. I'm defining how many variables do I have, which is basically the number of features, right? And I'm defining the number of classes. Here I'm considering 10 classes for the MNIST 10 digits. I'm defining how many sum nodes do I have at each level. So the number of sum nodes also defines how much expressivity your model has. So if you have a larger number of sum nodes, then you have a larger number of mixtures, which means you have more expressivity. You can also define how many distributions you need for each input variable, which also like increases your expressivity if you have more. What leaf distribution families to use. I'm calling it exponential family, but it's really what tractable distribution you're going to use here. We had specified it as the normal distribution, right? And what parameters you want to pass to that distribution. And the rest is just like training a neural model. So you have a model definition in PyTorch. If you print it, it looks like this is what it looks like, just like how you have like feed-forward layers and activations. Here you have what are called INSUM layer. And the INSUM operation is basically it's combining the sum and the product that you do into a single operation. We'll come to like how it is defined tomorrow, but I just wanted to give you the idea, right? It's more like a deep model here. How do you train it? Well, I can directly do a forward pass. I can sample data points from my data set. I can evaluate what the likelihood is by performing a forward pass on my model, right? And what is my loss function? My loss function is nothing but the log likelihood, right? And I can just do a backward pass, which is doing back propagation, computing the gradients, and then taking a step, right, to maximize the log likelihood. So when you train this, you can see that there's a significant reduction in the negative log likelihood, or like, this is the log likelihood. There's an improvement in the log likelihood, which means your model is fitting the data distribution. And how can you evaluate, like quantitatively visualize if what the model has learned is useful? Well, you can generate samples from it. Since it's an image, you can visualize the images to see if they are like of good quality and fidelity. So let's say, this is how the real data looks like on the top. And if I were to fit a model, a simple like PC with like 4 depth layer, and if I were to generate data from this model, this is what the data looks like. It's a bit blurry, but it's still something you can play around with and get better results on. So this is the data, but the real power in a tractable model comes from the ability to do inference, right? Tractable, you can do marginals and conditionals. And what is a good way to visualize that? So if I have images and I have occlusions in my images, for example, so the images I have regions that are missing, or I can have noise in my data, right? So if parts of pixels I have, let's say, subsets of pixels that are missing, then I can do conditional inference. What does conditional inference boils down to here? It's, can I write here? No. Okay, it's basically looking at the probability distribution over the missing pixels or the occluded pixels given the things that you have observed, right? So given the pixels that you have, that you know the value for, you have a conditional distribution over the remaining pixels. And if you have a tractable model, you can sample from these conditional distributions to fill in the values for those missing pixels for any arbitrary occlusions, right? You don't have to train a different model for a different type of occlusion, right? So let's see how that can be done with this model. Let's say I were to corrupt. So there's a parameter ncorrupt that like arbitrarily sets, in this case, 600 pixels to 0. Right, so I'm going to corrupt this particular image here, and this is what it looks like when I'm corrupting it. You can vary this and play around with it. Now what I would do is, okay, I'm interested in, what are we interested in? We are interested in marginalizing out the missing values and generating samples from the conditional distribution, right? So you can do that by, so in the Einstein network package, you can set the indices of the variables that you like to marginalize out. There's an explicit function called set marginalization index, right? And you can generate conditional samples over the corrupted pixels once you have set the pixels that you need to marginalize out, right? And if you were to sample from it, this is what it looks like. So this is what you had initially, and you were to sample, and you are interested in sampling the remaining pixels, right? So it's more like doing some sort of in-painting, but from a probabilistic standpoint, right? You're sampling from the conditional distribution. Right. So this is what you do, and you can also do approximate map with this model, where this. So the first example is just generating from the conditional distribution, right? P of corrupted pixels given non-corrupted pixels. You can also do map inference, where you're looking, okay, what are the values for my corrupted pixels that maximizes this this conditional density, right? Which is doing map. And when you do that, you tend to get slightly better in-painting results, right? But the whole point is, when you have such scenarios where you have occlusions or missing things, having a tractable model is very useful, right? So you can play around with this. So I think I will end the session here. We will start tomorrow with what exactly does this Einstein network look like? How have people come up with deep parameterizations for these probabilistic circuits, right? And what extensions have been proposed to make them competitive with the performance of deep generative models. We'll also look at some applications. All right, so that's, I think I'll close the session, but if you have any questions, you can feel free to ask now. By the way, the links to the notebooks would be available. We have a GitHub repository set up. I'll ask them to maybe email you or something. We have a GitHub repository link that has the slides and all the collab notebooks. All right. Questions? Good.